Okay, let's get right into it. Today, we're going to break down a paper that really fundamentally changed how machines see the world around them. It's called DeepLab, and it tackled this massive problem. How do you teach a computer to know not just what's in a picture, but to know exactly where every single thing is, right down to the pixel?
And that right there is the core question, isn't it? When you or I look at a photo, our brains just instantly separate the person from the bike from the road. It's effortless. But for a computer, it's all just a giant grid of colored dots. So the challenge, what researchers call semantic segmentation, is teaching that machine to color code every single one of those dots, every pixel, with a label like person or bicycle.
And this shows the magic when it all comes together. On the left, you've got the original, pretty complex scene, and on the right, that's the machine's understanding of it. Look at that. It is perfectly colored every single pixel that's part of a person one color and every pixel of the bike another. This is so much more than just basic pattern recognition. It's a deep, pixel-level comprehension of the world, and this is the incredible goal DeepLab set out to achieve.
And to really appreciate just how big of a breakthrough this was, we kind of have to understand what the world looked like before DeepLab. So let's take a quick step back in time.
You see, before this whole deep learning revolution, experts had to sit down and manually code detectors for things like edges, corners, and specific textures. These were called handcrafted features, and look, they were clever, but they were pretty limited. Then, deep convolutional neural networks, or DCNNs, came along, and you can think of these as networks that learn from examples. Instead of being told what an edge looks like, they just figure it out themselves by looking at millions of images. For telling a cat from a dog, this was an absolute game changer.
But, and here's the paradox, this new deep learning revolution, as amazing as it was for disclassifying an image, actually created a whole new set of problems for precise tasks like segmentation. In a way, it was a blurry revolution.
The great irony is that what made these networks so good at recognizing objects was that they were literally designed to throw away location information. Through steps like max pooling, which is kind of like squinting at an image to get the general gist, they would shrink the image down and down, focusing on the what and totally ignoring the where. And for a task that demands pixel-perfect location, well, this was a disaster. So the DeepLab authors really zeroed in on three core challenges that came from this. First, all that shrinking of the feature maps meant you just lost detail. It got fuzzy. Second, an object could be huge or tiny in an image, and the network had to be able to recognize it either way. And third, because of all that downsampling, the boundaries of the objects were just a blurry mess.
So, with the problems laid out so clearly, the team proposed this absolutely brilliant three-part solution. Let's break down each of these breakthroughs, because this is where it gets really cool. First up, they came up with something called atrous convolution, which you can just think of as convolution with holes. Instead of shrinking the image to see the bigger picture, they made their digital magnifying glass look at pixels with gaps in between them. Imagine trying to see the world through a sieve. You don't see every single little detail, but you get a much wider view without any extra effort. This let the network see more context without slowing everything down.
Okay, next, to handle objects of all different sizes, they created something called atrous spatial pyramid pooling, or ASPP. Now this is clever. They basically run several of those holy convolutions at the exact same time, but all with different hole sizes. It's like having a team of analysts looking at the same image. One is using a magnifying glass, another's a few feet back, and a third is looking from all the way across the room. By combining all those views, the network could spot an object whether it was tiny or took up the whole darn frame.
So, they'd solve the resolution problem and the scale problem. The network could see rich context and it could see objects of any size. But there was still a ghost in the machine. The output was, well, it was still kind of blobby. The DCNN was fantastic at getting the gist of an object, but it was just terrible at coloring inside the lines.
And this is where they brought in an older classic tool from the computer vision toolbox, the conditional random field, or CRF. The best way to think of this is like a meticulous artist who comes in at the end to clean up all the lines. The network gives it this blobby, rough draft. The CRF then looks at the original image and says, okay, wait a second. All these nearby pixels have a very similar blue color, so they should probably all be labeled as sky. It intelligently snaps those blurry boundaries to the sharp, actual edges it sees in the photo.
And just look at this slide. You can see the incredible difference the CRF makes. The before image is just a rough blob. I mean, the network knows there's a motorbike there, but all the fine details are lost. But then look at the after image. The outlines are now sharp, they're precise, and they perfectly match the object's real shape. It's night and day. And here it is again with the cyclists.
Before the CRF, the legs and the bike frame are basically one merged shape. But after, the system has recovered those impossibly fine details. You can see the space between the arm and the body, the gaps in the bike frame. It's just a massive, massive leap in quality.
So this combination of the three ideas, a atrous convolution, ASPP, and then a CRF at the end, it was elegant, it was clever. But did it actually work? Well, let's look at the numbers.
This was the headline number, 79.7%. That was the score they got on the main accuracy test, which is called mean intersection over union. It's basically a grade for how well the predicted shape overlaps with the real one. And this wasn't just a small step forward. This was a new world record.
And you know, a number is just a number until you see the competition. The previous leading methods, they were down in the mid-60s. DeepLab didn't just inch ahead, it blew right past them. A jump of over 13 percentage points on a benchmark like this is absolutely massive. They didn't just win the race, they completely changed the track.
So the crucial takeaway here is that it wasn't just accurate, it was also fast and relatively simple. At 8 frames per second, it was practical enough for real-world use. And its design, this powerful DCNN for getting the main features, combined with a classic CRF for refinement, was just such an elegant combination of the new and the old.
And that brings us to its legacy. Because, a groundbreaking paper is one thing, but a paper that shapes the entire field for years to come, that's something else entirely.
And hey, you don't have to take my word for it. The authors themselves noted this later on. They wrote, and I'm quoting here, "Most top-performing methods have adopted one or both of the key ingredients of our DeepLab system. That convolution with holes they invented, it became a standard tool for pretty much anyone doing this kind of detailed image analysis."
The influence of this work is literally all around us today. Autonomous vehicles use these exact principles to tell the difference between the road, a pedestrian, and another car. Medical AI uses it to precisely outline tumors in scans. And most famously, if you've ever used portrait mode on your smartphone, you've seen DeepLab's legacy in action. That perfect separation of you from the blurry background, that's a direct descendant of this work.
DeepLab gave machines a much, much sharper vision of our world. It was a key step towards systems that don't just classify images, but genuinely perceive the structure within them. And that really leaves us with a final question. Now that machines are getting so good at seeing the where, what's the next frontier in teaching them to understand the why?
This is for entertainment purposes only.